Hello everyone, my name is Alejandro Job and I'm going to explain how to design power electronic converters with AI and automated simulations. Perhaps you, like me, are sick of hearing about AI everywhere, but I will try to prove how can AI improve in the simulation and the results and be meaningful in the fields of power electronics. So let's introduce briefly the company I work for, which is Technalia. And also it makes this work possible. We are more than 1,500 people working there from many different countries and full of PhDs and experts in their fields such as AI, health, hydrogen, engineering, and many others. Okay, this presentation is divided into the following topics: the context and the motivation, an explanation of the workflow, some results, and eventually the conclusions and the future work. So let's start with the context. Up to now, when you design a power electronic converter, you do it either analytically with analytical equations or by simulation typically. This is most of the time a slow process when ideal components are assumed and many design parameters come into play. But what I'm proposing here is totally different. In this case, I'm picking a dual active bridge as an example for this solution, which makes use of the phase shift modulation. Why? Because it has many degrees of freedom since it is isolated. Its soft switching depends on the operating point, and many different modulation strategies can be applied to this topology. It has also been mentioned many times in this conference. So I show here a picture of a schematic picture of this topology and some images of the waveforms. For this study, rectangular modulation, also called phase shift modulation, has been employed. So why using AI and why SIMBA for this solution? Because they can provide automated simulations and workflow for both the parameters and operating points. SIMBA also offers a seamless integration between Python and power electronics, and the results are based on real components, taking into account all of their non-linearities. And perhaps the most important, because here in Technalia, we have an impressive supercomputer with these features, which is ideal for this application. Okay. Apart from that, we count with real prototypes to validate the results. Their main characteristics are the following. Also, we have the replica, the software replica in SIMBA. And why having these prototypes? It's important because after having designed the theoretical design with AI, we can test it in the reality and change some components and validate the results. For example, the power losses, voltage and current ripples, and so on and so forth. Okay, so let's start with the workflow. Firstly, we begin with some requirements, then we proceed with the automated simulations. Afterwards, we perform the AI training and test, and finally, the optimization and validation is carried out. So let's explain a bit further the workflow. We start from some design parameters or degrees of freedom, which are the switching frequency, the output capacitance, and the leakage inductance. Then, for all of the simulations, we collect the following data: the junction temperatures, power losses, and voltage and current ripples, which will be later used for the AI training. Here, there are different possible goals or objectives, which are the efficiency, power density, reliability. For example, if you want to optimize the efficiency, you have to reduce the power losses. You want to increment the power density, you reduce the volume components, passive components, for example, and to maximize their reliability, well, in this case, for example, you can um, reduce the delta T and the main junction temperature of the MOSFETs, for example. For this study, the optimization of the efficiency has been taken. Okay, and as for the process, more specifically, we begin with a range of parameters and values which are introduced in MATLAB. Then we perform the simulations with a script which launches SIMBA and save the results, which are later used for training the neural network and obtain the results. Okay, in this slide, in a higher detail, you can see how is the simulation sweep process. Okay, and let's talk a bit about the AI algorithms utilized here. On the one hand, the AI algorithm that has been used is the following. In this picture, where, for example, we extract the power losses as a function of the design parameters for all of the operating points, and then we save the results. And afterwards, since we have a continuous set of variables, we employ a genetic algorithm to optimize the results. In this case, to maximize the efficiency. Okay, let's proceed to show some results. Here, yeah, we have seen that we requires no supervision for this design process. Also, the behavior has been evaluated at both soft switching and non-soft switching condition, and we obtain a set of parameters derived from the optimized efficiency. In this case, 100 watts corresponds to the condition of no zero voltage switching, and 25 kilowatts, which is almost full load, corresponds to the soft switching condition. Okay, more specifically, we validate the errors of this methodology for both the training and the test set, and we ensure that the hyperparameters chosen in this solution are selected properly for the training of the neural network. Apart from that, we've got no overfitting nor underfitting. Okay, and to provide some metrics, it turns out that the results are below 5% for a training and the test set in both conditions, soft switching and non-soft switching. And also, it turns out also that the results vary very lightly, depending on the neural network you use when trying to increase it. So the result from the conclusion from that is that a bigger and more complex AI architecture many times doesn't have to improve the results. Okay, so to sum up, I'll talk about a bit the conclusions and the future work. So an improvement in terms of efficiency has been achieved here by using a novel methodology. Also, we have a proof of concept, and we obtain an error below 10% for this AI-driven design methodology. Okay, and as part of our planned future work, we have planned to integrate the magnetic design in our process, also to extend it to other topologies, try to search for new configurations, and of course, utilize a real component database. Why? Because it doesn't make much sense. For example, if one result is a capacitor of a non-existing value, for example, and also to be able to consider the size of the components. Okay. And to provide some bibliography, I have here some references about the dual active bridge and this AI-driven design methodology. Okay, and that's all. Thank you very much for your attention, and I hope you have learned something new.